Today, my partner and I are going to talk about the physics of figure skating.
It's not a topic that we hear about often, but in figure skating, physics intervene in every aspect. The jumps, the spins, even the landing, all of them wouldn't be possible without it. The most important item in figure skating are the skates. The skates consist of a boot and a blade that is fixed with screws to the sole. Blades are roughly 4.8 mm thick. When viewed from the side, the blade is not flat but slightly curved, forming an arc. The blade is also hollow. It has a groove on the bottom of the blade that creates two distinct edges, inside and outside. Skates also have a set of large, jagged teeth called toothpicks on the front of the blade. The toothpicks are used primarily in jumping, footwork, and spins. Firstly, to start moving, a skater must apply force into the ice. This force is created in the muscles between the knee and the hip joint. Then is transferred through the lower part of the leg and the ankle joint. By slightly pushing that force and leaning into an edge of the skate, the skater path becomes a circle, creating angular momentum, making the blade move faster across the ice. What about the jump itself?
The jump itself is divided into three categories: the takeoff, the spin, and the landing. For the takeoff, essentially, as a skater is coming off the ice and they're pushing down to get their vertical velocity, they also need to push against the ice more sideways, so they can start turning on the ice and to get some rotational momentum. Just then, they're rising in the air. Without a doubt, they have to be in the air long enough to complete however many revolutions they're trying to do. The time they're in the air is directly related to the jump height, and that is pretty much related to how much vertical velocity they can get when they jump off the ice. But what makes figure skating so impressive are all the spins and the landing, of course. Once a skater leaps into the air, they're stuck with however much angular momentum they've created, given that no outside force is applied. But they can still change one thing: the moment of inertia. The moment of inertia determines how easy it is for an object to speed up or slow down, and describes the resistance that a force is working against. A larger moment of inertia, like when a skater extends their arms, will result in a slower rotational speed, but a smaller moment of inertia, like when a skater hugs their arms into their body tightly, will lead to a faster spin. However, the skater still has to land the leaps. It's estimated that a skater impacts the ice with a force 5 to 8 times their body weight and must dissipate the majority of their energy in the landing, which takes place over a very small period of time. Skaters can't spread the dissipation of energy over a longer time period and over a bigger range of motion, so without proper training and technique, it could lead to injuries in their spine.
In conclusion, the jump amounts to three components. How much angular momentum do you leave the ice with? How small can you make your moment of inertia in the air? And how much time you can spend in the air? This requires a careful balance of all of them.